Hey everybody, Johnny here. In this video, we're going to take a look at how we can create root-like structures like this that fill up a volume. In this instance, I'm using a Suzanne head to define the shape of these roots. This is a multi-step process and uses some concepts that I've used in some of my other videos as well. So without further ado, let's jump right into it. To make this idea work, I started with the concept that I needed there to be a grid of points inside of my mesh, and those points needed to be connected to each other using edges. So for example, if I wanted just to have a cube like this, I could add a grid, let's say 4x4. Then I would remove all of the faces and end up with something like this. So it's a 3D grid of vertices, and all of those vertices are connected to their adjacent vertices. Then I could simply apply some randomness to these points, and then use these edges to determine some shortest paths. That's the first step I wanted to do in my geometry node tree. I'll delete this and add in an object that I can use. For simplicity, we're just going to use a UV sphere. I'll add a new node tree and disconnect the input geometry for now. The first thing we need to do is figure out how we're going to generate our grid of connected points, which I'll refer to as an edge lattice. That's just my name that I've given it. To start with, I'm going to use a mesh primitive grid. I'll drop this into a group because we're going to make a node group out of our edge lattice. Now, in addition to a size and vertex count on the X and Y plane, we're going to also want a Z size and a vertices Z. So we'll go ahead and add those right away. Now, just like we did before, we'll want to delete the faces of this grid and just leave the edges and the points. So we'll use a delete geometry node and set it to only faces. So now I have a 2D grid of points and edges. The next thing we'll want to do is to duplicate this and stack it on top of each other as many times as we indicate by our vertices Z socket. We'll use a duplicate elements node and set it to edges. We want to duplicate this as many times as we have set on vertices Z. We'll set it to 3 here to start with, and we'll set the Z size to 1000 millimeters. We'll want to make sure to set our defaults here as well. Now, because we haven't done anything with our duplicates, they're all stacked in the same position. So we're going to want to set the position of our duplicates. We'll use a set position node, and we'll want to set the Z position of our points based on the duplicate index. So we'll use a combine XYZ node and plug our duplicate index into Z. This gets us close to what we want, but our only problem is each layer is stacked 1 unit above each other, no matter what our other settings are. So we'll need to scale these based on the total size in the Z position that we want. To get the scaling factor that we need, we'll take whatever size we've asked for along the Z axis, divide it by the amount of segments that we're going to need, in this case 2, because the first one will be at 0, the next one will be at 1, the next one will be at 2, and then we'll take that and multiply that by the duplicate index. So if we take our size Z and divide it by the vertices Z, here our default was 1000 for the size, and we divide that by 3. So each segment would be 333.3 repeating. However, if we multiply that by our duplicate index, this one will be at 0, this one will be at 33, and this one will be at 66. So that's not quite what we want. We actually want the count of how many spaces are between the layers, not the number of layers. So we simply need to subtract 1 from vertices Z to get the right factor. So now the factor is going to be 1000 divided by 2, which is 500. So duplicate 0 will be 0, duplicate 1 will be 500, and duplicate 2 will be 1000. So that's what we want here. One tip for keeping your node trees cleaner is when we do something like this, where we're just subtracting 1 from something. One thing you can do is rename this node by pressing F2 and calling it something like subtract 1. Now, if you collapse this node, even though this isn't connected to anything, you know that this is just subtracting 1. Now, if you need to subtract 1 from anything else, you can just duplicate this node and you don't have to have a fully open node to accomplish subtracting 1. Now that we have this factor, we can simply multiply the duplicate index by it. There. That looks a lot better. Now that we have our layers, we simply need to add upright supports through each point of the grid. We can do that by taking this bottom layer and extruding all of the points upwards until they meet the top layer. And then we'll cut those extrusions to match the number of layers in the middle. So first we need a copy of this bottom layer. The bottom layer was created using this grid node, so we'll bring it down here. Now we only want the points, we don't want any of the original edges. So I'm going to use another delete geometry node. And this time set it to only edges and faces. So now all we'll be left with are the points of this bottom layer. We'll take those points and we'll extrude them with a mesh extrude mesh node. We'll set the mode to vertices. Now let's take the output of this extrude mesh node and connect it with this node up here so that we get both in the output. The next thing we see is that our points are extruding outwards and not upwards. To change the direction of the extrusion, we simply need to mess with the offset. If we attach an input vector and plug it into the offset and change it so that the offset is 0, 0, 1, that means it will only go up in the Z direction. This is getting us closer to what we need. However, if we increase the Z size, we notice that our extrusions don't match up anymore. So we need to take the offset scale of our extrusion and match that up with our Z size. We're getting much closer now. So let's go ahead and merge these two channels that we've created with a merge by distance node. If we duplicate this mesh now and apply its node tree, we can see what we've got. If I take one of these corners and move it away, we see that it is connected to the bottom and the top, but it's not connected at all to the middle. What we'll need to do is take each of these uprights and split it the number of times that we have middle layers, which would be our vertices Z count minus 2, the 2 being the top layer and the bottom layer, because we're already connected to those. You might think that you'd want to use a mesh subdivide node on our uprights. The only problem with that is that we'll only subdivide by levels of 2. So we'd get 2 subdivisions, 4, 8, and so on. If we want a specific count of subdivisions, we're going to need to convert these to curves first. So we'll take our uprights and add a mesh to curve node. Now we can use a subdivide curve node to give an exact amount of subdivisions that we want between the beginning and the end. So I'll choose a curve, subdivide curve. And like I said before, the number of cuts we want is the amount of middle layers. So we take the total amount of layers, subtract the bottom and the top, and that leaves us with the middle. If I take my vertices Z and plug it into the number of cuts, and subtract 2 from it, which I'll grab this subtract 1, bring it down here, and change it to 2. I should now have 1 cut in the middle of each of these upright lines. So I can take these curves and turn them back into meshes with a curve to mesh node. Now if I take this object and duplicate it and apply its node tree, you'll see that these vertices are all connected properly. Now that we have this, let's go ahead and rename this to Edge Lattice. And we'll mark it as an asset. Now that we have this, we'll want to match the size of this lattice with whatever incoming geometry we have. We can of course get that size from the bounding box of our incoming geometry. If we simply subtract the minimum from the maximum, that will give us a size. We can separate XYZ and plug that into the size of our edge lattice. You'll notice here that our edge lattice is 2 by 2 by 2, which is the bounding box size of our sphere. However, they aren't centered at the same spot. That's because we've only taken the size of our sphere and applied that to our edge lattice. The center points are not at the same spot. If we want to align the bounding boxes of our edge lattice and our sphere, we could simply take the bounding box of our edge lattice and subtract its minimum position from the minimum position of our original geometry. This will simply give us a vector that all of the positions of our edge lattice will have to move in order so that the two bottom corners of the two geometries will line up. If we use a set position node on our edge lattice and use this vector as the offset, our edge lattice will now match up with our incoming geometry. So if I move my incoming geometry over here and leave the origin here, you'll notice my edge lattice moves accordingly. Now we can take all of these nodes and group them together. And we can call this one aligned edge lattice. So now we can stick in an original geometry and we get out an edge lattice that matches its bounding box. The only other options we might want to expose on this node is the resolution of our edge lattice. Now we have full control in all dimensions. The next step we're going to want to do is to be able to remove the points of this edge lattice that are outside of our source geometry. I did another video previously that looked at a method for doing this for randomly generated points. I'll put a link in the description so that you can check that one out. I'm going to go through it pretty quickly, so if you want a deeper explanation, be sure to check out that video. The gist of the idea is that we take our original geometry and transfer a couple of attributes. The first attribute being a normal, and the second attribute being a position. The attributes will be transferred based on the points of our edge lattice. So we'll get the normal of the nearest face to that edge lattice point, and we'll get the position on the nearest face to each point of our edge lattice. If we subtract this position that we've transferred from the original geometry face from the position of the point in the edge lattice, that will give us a vector. That vector goes from that nearest face to the point in our edge lattice. We compare that to the normal of that face on the original geometry. And if they're pointing in the same direction, that means that the point on our edge lattice is outside of the mesh. And if they're pointing in opposite directions, that means the point would be inside the mesh. We determine if they're pointing the same direction by using the dot product. So I'll take this normal and use the dot product. I'll also add a subtract node and subtract the position on the face from the position on our edge lattice. If this value is positive, that means the point on our edge lattice is outside of our mesh, and so we want to delete it. I'll add a delete geometry node and add a compare node to our dot product. So when this is greater than 0, we'll delete. One thing that can be confusing for some people is why I'm using two position nodes here and how it knows where to get the position from. You can look at it this way. If we follow this geometry from our edge lattice all the way down here, and then we go backwards from the delete geometry, we get to this position node. And there's no other geometry that's being introduced into the chain between here and here. So this position goes with this geometry. However, once we get back to the transfer attribute, The transfer attribute is actually getting its information from this geometry. So this normal and this position are coming from this geometry input. Because this is true, we could connect this position here and it would still work, because it would interpret the two position nodes separately for each place they connect. But for clarity, I'm going to leave it like this. So now if we look here, we're getting the shape of the sphere just using our edge lattice. If I increase this resolution, you can see it's doing exactly what we want. Now that we have an edge lattice in the proper shape, we can start applying our shortest edge path node. So to this geometry, we'll add a mesh, shortest edge path node, and we'll add a mesh, edge path to curves. The edge paths to curves is what gets plugged into our geometry line, and then we plug in the next vertex index to here. First, we're going to have to choose what our start vertices are. Let's do something simple, like if the position z component is less than a certain amount, then that point will be a start vertex. And then we'll do the opposite for the end vertex. We'll change this to greater than and plug it into the z. Now right now, all of these vertices are greater than 0. So I'm going to move these down here. Now these don't look very good yet, because we haven't assigned an edge cost. The edge cost we want to assign is the length of each edge. So to get the length of each edge, we'll simply take the edge vertices node and take the distance from position 1 to position 2. We use a vector math node set to distance to do this. Now the results we're getting might not be very interesting just yet. Let's go ahead and change these curves back to meshes using a circle profile. We'll add a curve to mesh node, and a curve primitive circle. We'll set the resolution low to something like 4 and plug this in here, and make sure to reduce the radius. You can play with your settings here to start getting some interesting shapes. Now, because we're only going top to bottom, we might not get something very interesting. We could of course change this to see what else we could get. Another thing we could do is add an empty that we can use as a comparison point. From here, I could say something like this. We want our start vertices to be any that are within a certain distance of this empty. I'll drag the empty into my node tree and say where the distance of the location to the point in our lattice is less than a certain amount, that will be end vertex. And we'll have the start vertex be all points. Or we could add another empty, pull it into our node tree, and do the same thing for the start vertex. Now, because our lattice is very squared off, we're not getting very interesting results, but we can fix that. We could take our edge lattice and add some randomness to the positions. We'll add a geometry, set position node, add a utilities random value node, and set it to vector, and connect this to the offset. Now we don't want this to be very large, but enough to give us some variation. We also want to smooth these out, because when we use this edge paths to curves, it creates polycurves, not nice smooth Bezier curves. So what we can do to this curve output is add a curve, set spline type, and change it to Bezier. Now because we changed this from a polycurve, the Bezier handles are all set as vector. So we'll add a curve, set handle type, and now we've got smoother curves. I'm going to edit my main shape. And I'm going to increase the resolution of my lattice. Now we're starting to get something interesting. Depending on what you're going for, you might want to have your lines taper out as they get towards the end. We could of course do this with a set curve radius. Then we can use a spline parameter node and the factor. And we can start to get something interesting. If I were to take this shape and replace it with Suzanne, and then remove my connection to this second empty that's running the start vertices, again, you can see I'm starting to get something more interesting. However, because the randomness isn't that much, if you look straight on, you can still see the grid shape pretty well. So another thing you can do is after you've added this randomness, you can do some merging of vertices. As you increase this, the vertices that have been moved closer and closer together are going to get merged, making some more unique paths. And as you can see, this really starts to get away from the grid pattern. Also, the more randomness you add is going to add more interest. Of course, how you select where your start and end vertices are going to be is going to greatly affect how your end result turns out. You're going to want to try as many different things as you can. There's lots of different ways to make this really interesting. Now be aware that you'll want to be very careful when increasing the resolution of your edge lattice, because if it gets too big too quickly, it may grind your Blender instance to a halt. This can get pretty resource intensive pretty quickly. However, with a little trial and error, I think you're going to be able to come up with some pretty cool things. Anyhow, I hope this wasn't overly confusing, and I hope you got something out of it. This new shortest edge paths node is going to be helping people create some really interesting things, and I hope my idea of an edge lattice will help you think of some ways that you can use it in even more creative ways. Thanks for watching, hope this inspires you to make something awesome, and until next time, I'll catch you later.